This is a presentation of our work on hardware-software contracts for secure speculation. This is a joint work with Boris Kopp from Microsoft Research, Jan Reinecke from Saarland University, and Pepe Vila from Imdea Software. Speculative execution attacks such as Spectre exploit speculative execution, an optimization implemented in modern CPUs to leak sensitive information. Since the discovery of Spectre, researchers have been working on countermeasures to mitigate these attacks. As an example, this is a collection of a few recent mechanisms for secure speculation. Let's look at how they work on a few examples. So this is the standard Spectre v1 example. When executing the branch instruction, the processor might speculate on the branch outcome and continue the execution based on this speculation. For instance, if X is out of bound, the processor might anyway speculatively execute the memory accesses, which results in leaking an arbitrary memory location, pointed by A of X here, through the data cache. Other countermeasures implement different ways of blocking such a leak. For instance, load delay countermeasures, such as those proposed by Sakalis and others, prevent the leak by delaying the first load until the branch instruction is resolved. In contrast, hardware taint tracking countermeasures taint the result of the first memory access and delay the second one, thereby preventing the transmission, namely the encoding into the cache, of the information. Consider now this slightly different example. Here, the first load happens non-speculatively. Now, the first two countermeasures still prevent the leak since they delay the execution of the second load. However, taint tracking based mechanisms like NDA and STT do not prevent this leak because the first memory access is not tainted, since it is not transient, and therefore the second access is not delayed. As a result, this leads to speculatively leaking A of X. So, as our simple examples have shown, these defenses block different classes of speculative leaks and they provide different security guarantees. However, we currently lack a uniform way of precisely characterizing these security guarantees, and as a result, we also lack a precise understanding of how programmers can leverage these defenses to build secure systems. In this paper, we present a framework for formalizing hardware-software contracts that support principled code design for secure speculation. As we will see in this talk, our contracts can precisely characterize the security guarantees provided by recent hardware proposals for secure speculation, and they provide program-level properties formalizing how to leverage these hardware guarantees to achieve global end-to-end security. Let's look at our framework for specifying contracts. In our framework, a contract specifies which program executions a side-channel adversary can distinguish by observing the microarchitectural state. In particular, contracts capture security guarantees of hardware in a simple mechanism-independent manner. That is, they abstract away from intricate microarchitectural details. In this way, they also act as a basis for principled secure programming, since they enable understanding how to securely program different hardware platforms. A contract is formalized as a labeled ISA semantics, where steps in the semantics are associated with observations tau that expose security-relevant microarchitectural events. Given a program P and an architectural state sigma, we have contract traces, that is, the sequence of observations associated with executing P on sigma according to the contract. In our paper, we formalize processor using hardware states that consist of architectural state sigma extended with microarchitectural state mu that describe the state of microarchitectural components like caches and branch predictors, and the hardware semantics that describes how states are modified during the computation. Finally, we consider attackers that observe part of the microarchitectural state during computation. This is captured by what we call hardware traces. We can now formalize contract satisfaction. We say that the hardware satisfy a contract if for all programs P and states sigma sigma prime, whenever the contract produces the same traces, then the corresponding hardware traces must be the same. That is, whenever a hardware satisfies a contract traces capture which executions are guaranteed to be indistinguishable to an attacker. Our contracts for secure speculation are defined in terms of an execution mode, which describes how programs are executed, and an observer mode, which describes what kind of information a contract exposes during the execution. As execution mode, we consider a sec mode where programs are executed sequentially, and the spec mode where program execution also explores mispredicted paths, therefore exposing the effects of transient instructions. As observer mode, which describes what information is disclosed during the execution, we consider three variants. The PC mode discloses changes to the program counter during execution. The CT mode additionally discloses the address of memory operations, and it captures the standard constant time observer often used when reasoning about the absence of side channels in cryptographic code. Finally, the ARC mode additionally discloses the values loaded from memory. As a result, this mode effectively discloses the values of all registers during the execution. By combining all these modes, we obtain several different contracts, depicted here. In our framework, contracts can be compared in terms of the security guarantees they offer, where a contract C is stronger than another contract C' if C leaks less information than C', represented here with an arrow from C' to C. So, this picture illustrates the relations between secure speculation contracts. For instance, the bottom contract leaks everything and provides no security guarantees. In contrast, the top contract leaks nothing, and it is associated with an ideal processor that does not leak information through side channels. The SecCT contract corresponds to the usual constant time model, and it only leaks the address of non-speculative loads, stores, and instruction fetches. The SecArc contract, which additionally leaks the loaded values, provide weaker guarantees as represented by the arrow here. Similarly, the SpecCT contract, which additionally leaks the addresses of speculative loads, stores, and instruction fetches, also provides weaker guarantees. However, SecArc and SpecCT are incomparable in terms of leaks. As I will show next, we can use the secure speculation contracts to compare guarantees provided by different hardware defenses. As a basis of our analysis, we developed a formal model of a simple processor. The processor supports both speculative and out-of-order execution. It has a 3-stage pipeline with fetch, execute, and retire stages, and it is parametric in the branch prediction strategy as well as in the memory hierarchy. On top of this model, we implemented several hardware-level countermeasures, and we studied their security using contracts. Let's first consider the vanilla processor without countermeasures. This processor is vulnerable to Spectre-style attacks. When executing this branch instruction, the processor might mispredict the outcome of the branch and speculatively execute the memory accesses even when x is out of bounds, thereby speculatively leaking a of x. So, without countermeasures, our processor leaks the address of all speculative and non-speculative loads, stores, and instruction fetches. As a result, it satisfies only the weak SpecCT contract. The first countermeasure we analyze is completely disabling speculative and out-of-order execution. In this case, the processor executes instructions sequentially, where each instruction is fetched, executed, and retired before moving to the next one. Obviously, this countermeasure prevents all speculative leaks. As a result, it satisfies the strong SecCT contract, which only discloses the address of loads, stores, and instruction fetches over non-speculative executions. The second countermeasure that we analyze is the eager delay of speculative loads proposed by Sakalis and others. This countermeasure delays loads until all sources of speculation are resolved. We formalize this by modifying our processor to execute load operations only when all prior branch instructions in the reorder buffer have already been resolved. So, what are the guarantees offered by eager load delay? In the standard Spectre example, the memory accesses are delayed until the branch instruction is resolved, and therefore there is no speculative leak. However, consider a variant where we first access a of x and then we use the retrieved value as part of a control flow statement. This can potentially leak the value of a of x through control flow. The execution of the second branch instruction is not delayed since the eager delay countermeasure applies only to data loads. Therefore, we can still speculatively leak the value of a of x. For instance, skip is loaded into the instruction cache only if a of x is 0. In general, the countermeasure successfully blocks speculative leaks involving load operations, but it does not block speculative leaks through control flow operations. As a result, eager load delay satisfies the SecArc and the SecSpecCT contracts. The former captures that it can only leak data retrieved non-speculatively, whereas the latter captures that it does not block speculative leaks through control flow operations. Finally, we analyzed hardware taint tracking mechanisms like STT and NDA. These mechanisms taint all speculatively loaded data as unsafe. They propagate taint through the computation, and whenever operations are no longer transient, the taint is removed. Finally, these mechanisms selectively delay tainted operation to avoid leaks. So, what are the guarantees offered by these mechanisms? For the standard spectre snippet, the mechanisms tag Z, the result of the first memory access, as unsafe. Therefore, the second memory access is delayed since Z is unsafe until the taint is downgraded to safe, that is, when the branch instruction gets resolved. Therefore, in this case, there are no speculative leaks for both STT and NDA. Consider, however, a variant of the spectre snippet where the first memory access happens before the branch instruction. Here, Z is tagged as safe since the load is non-transient, and therefore neither NDA nor STT delay the second memory access. So A of X is leaked speculatively. So the summary is that while both countermeasures are effective at preventing speculative leaks of speculatively accessed data, they fail in preventing speculative leaks of non-transiently accessed information. As a result, they satisfy the SecArc and the SpecCity contracts. So, this is the high-level overview of our results. Without countermeasures, processors satisfy only the weak SpecCity contract. The Sec countermeasure, which disables speculative and out-of-order execution, satisfies the strong SecCity contract. The load delay countermeasure, which delays loads until all sources of speculation are resolved, satisfies the weaker SecArc and SecSpecCity PC contracts. Finally, taint tracking mechanisms satisfy the SecArc and SpecCity contracts. So, our contracts allows us to give precise security guarantees for existing countermeasures and to order these guarantees. Disabling speculative execution provides stronger guarantees than eager load delay, which in turn provides stronger guarantees than ardor-based taint tracking solutions. In the paper, we provide models and proofs for all these results. Contracts provide a basis for secure programming and for leveraging the security guarantees offered by different classes of hardware countermeasures. We consider two flavors of secure programming. First, we consider a constant time scenario where the goal is ensuring that a benign program does not leak confidential data to a side channel adversary. Second, we consider a sandboxing scenario where the goal is preventing a potentially malicious program from accessing confidential data outside of its sandbox. In the paper, we generalize traditional constant time and sandboxing notions to work for arbitrary contracts, since traditional notions are not enough in a post-spectral world where processor might leak through speculatively executed instructions. This table summarizes whether programs that satisfy traditional notions can be run securely on a processor that satisfies a given contract. In particular, a checkmark denotes that programs that satisfy the traditional notions can be run securely, while a crossmark denotes that programs need to satisfy additional security checks beyond traditional constant time and sandboxing. So, for the SecCity contract, all programs that satisfy traditional constant time and sandboxing, which can be checked using existing tools, can be run securely. For the SecArc contract, additional security checks are needed only for constant time but not for sandboxing. Finally, for the SpecCity contract, additional security checks are needed for both flavors of secure programming. In particular, one would need to check that programs satisfy a class of properties called speculative non-interference. In the paper, we present full security definitions, we describe in detail the additional security checks needed to run programs securely, and we discuss how existing tools can be repurposed to reason about general constant time and sandboxing. So, what are the practical implications of this? Consider a processor implementing hardware taint tracking. This processor satisfies the SecArc and the SpecCity contracts. This processor is well suited for sandboxing since any traditionally sandboxed program can be run securely without further restrictions. However, it is not enough for constant time. Indeed, traditional constant time programs would have to satisfy further constraints to be run securely. So, to conclude, I presented a framework for expressing hardware software contracts. I illustrated how the framework can be instantiated to talk about secure speculation. I then showed how to use the framework to characterize and compare the guarantees provided by a class of hardware-level countermeasures. Finally, I discussed how the framework enables hardware-software co-design, and I've shown how it can be used to automatically reason about different flavors of secure programming by leveraging existing tools. Thanks for your attention.